Today we're going to talk about optimizing the surface area of a cylinder. Well, cylinder problems are interesting and they're very common in calculus. So I want to show you what you have to do with a cylinder in order to talk about the surface area of it. Maybe this has been shown to you in your geometry class, but in case it hasn't, I'll show you again. So what I have created here is this is just a cylinder. I just took a sheet of paper and I put the ends together. So here's the cylinder. And if I want to figure out what the surface area of this cylinder is, and I'm going to include a top and a bottom, what I would have to do is I would have to calculate the area of the top, which is just pi r squared, and the area of the bottom, which is another pi r squared. And then I'd have to calculate the surface area of this round part of it. To calculate the surface area of this round part, what I want to do is I want to actually cut this sheet of paper. So if I were to cut this sheet of paper along its length, what I get out of it is a rectangle. So I've cut this cylinder and now I'm just going to flatten it out. And now I have just a rectangular sheet of paper. And the area of this, which was put together like this, turns out to be really just the area of a rectangle. And the area of this rectangle is the height of the cylinder times this length, which, because it's the top of a circle, the length around the top of the circle is just 2 pi r because it's the circumference. 2 pi r is the circumference, excuse me. So to get the circumference, you need to know the radius. So 2 pi times the radius is the length of the cylinder and the height is h. So I'll just show you that on this picture. And I'll tell you what the problem that we're going to go through here is. We have a cylindrical soup can. Let's imagine that that sheet of paper was a soup can, and it has a volume of 355 cubic centimeters. And what our job is to find the dimensions, which is the radius and the height of that cylinder, that minimizes the surface area. Usually you want to minimize surface area so you can get the least amount of material, which would minimize cost when you're trying to do a cost of, if you're trying to manufacture a whole bunch of soup cans, you want to minimize the cost. So you minimize the surface area, but you still have a constraint to work with, a volume of 355 cubic centimeters. So like these problems always usually have to read it at least twice, maybe 3-4 times really to figure out what you have. And then if you could draw yourself a picture, that would be very helpful. So this picture has been drawn for us. Here's the soup can, and that was like the sheet of paper that I rolled up for you. And the soup can has a height and it has a radius. And if we were to cut the soup can along this line and to flatten it out, here's the circumference of the top of this soup can times the height. So you've got a surface area here of this part of it, and then you have the surface area of the top part, which is just pi r squared, and then you have the bottom part also. So the area, the surface area that we're trying to minimize is 2 pi r squared, because you have 2 pi r squareds. That's the top and the bottom. So you have to multiply it by 2 to get both of them. And then the height times the length is 2 pi r times the height. So that's the surface area. That's what we're trying to minimize. Excuse me. All right, so I'll give you a couple minutes, or you might want to just shut the video off so you can draw this picture, write down the formula, and just know in your head that you're trying to minimize this. What we have here is we have an equation that we're trying to minimize in 2 variables. We have the height and we have the radius. But if we're trying to minimize or maximize something, we only can have one variable, because when we take the derivative, we're going to take the derivative with respect to only one variable. And so in order to change either the height into terms of R or R into the terms of height, what we're going to do is look at our constraint. And our constraint is that this soup can has a volume of 355. Oh, we've already assigned a variable for each of the quantities. R is the radius and H is the height. And the surface area that we're trying to minimize, like I said, was pi r squared times 2 plus 2 pi RH. Now the constraint that we have is that the volume, and the volume of a cylinder is pi r squared H. So that's something that, oh, let me focus this a little bit better. The volume of this soup can is pi r squared H. That's the volume of a cylinder. And they told us that 355 is the volume. So we can write this out. That is our constraint. And then we're going to use this constraint either to solve it for R or to solve it for H. But because R is squared, I think I'd rather solve it for H. It would make our life a lot easier, so then we wouldn't have a square root in our equation. So we're going to solve this for H just by dividing both sides by pi r squared. So our height is set up in terms of R. And this is what we can use to go substitute back into our original equation. So we can take this H out of here, and in place of the H we can put 355 divided by pi r squared. So that's what we have down here, is we have the 2 pi r squared plus 2 pi r times H, and that H came in here. You can just forget about that line. Now the next thing we're going to do is simplify this equation. So the pi's can cancel. You got a pi in the numerator and a pi in the denominator, and you've got an r in the numerator, and one of those two r's can disappear. And now we're left with 2 times 355 all over r, so we have 2 pi r squared. 355 times 2 is 710 over r. So that's the surface area. So this is what we're trying to minimize. Oops, minimize. So what we have to do is take the derivative. So we're going to take s prime. So in order to take the derivative, hopefully you're able to take a derivative now, and the s prime turns out to be 4 pi r minus 710 over r squared when you take the derivative of each of the terms of s. So when we had s prime is equal to 4 pi r minus 710 over r squared, you set the derivative equal to 0, and then you can just add 710 over r squared to both sides. And now our job is just to solve this for r. Well, we want to get r on one side of the equation, so you're going to multiply both sides by r squared. And if you multiply this by r squared, that r squared disappears on the bottom. And then you can divide both sides by 4 pi. So the 4 pi disappears here. And what you're left with is 710 r squared over 4 pi. I'm sorry, r squareds cancel out. What you're left here is 710 over 4 pi is equal to r squared times r, which is just r cubed. So when we solve this for r cubed is equal to 710 over 4 pi. All you have to do is take the cubed root in your calculator, the cubed root of 710 over 4 pi. And numerically, that turns out to be about 3.84. I would probably take that to another decimal place, because usually we have to take that to 3 decimal places. Oops. The cubed root of 710 divided by 4 times pi. Oops, I did something wrong there. Anyways, 3.84, there's probably another decimal place. And now the next step, step 8, this is in small letters, I don't know why, but determine if it's an absolute max or a min. We have to do a sign table, so we have an s prime sign table here. We put the 3.8 for the critical number, and then we do a couple of test points into the derivative. So if you plug in, I would plug in r is equal to 1 up here, and that becomes a negative number because you just have 4 pi minus 710, which turns into negative. And then I would just put something really big, positive number. So that turns out, the bigger the r gets down here, the smaller this number gets. So this is a negligible and this becomes big. So that would be a positive. Without a calculator, I would be able to determine that. So this looks like we have a plus minus, and that means that the graph will go down and then it'll come up, which tells us we have a minimum value for r. So we don't have endpoints. The only thing that we know about the domain is that the radius has got to be positive. So we don't have to worry about negative numbers, and this will just continue to grow and grow. So 3.84 is the absolute minimum point of this. So that's what this explains. It goes from minus to positive, so it corresponds to a relative min. You can also look at the graph of this. If you put into y equals 2 pi x squared plus 710 over, well, 710 over r, this is the original surface area. You can get a minimum surface area from the graph if you do second calc min. And so now we have to go back to the constraint equation so we can solve this for h. But we know what r is, we can put that in. And our height is 7.67. So we will write a sentence to conclude this whole problem, that the minimum surface area occurs, I should say occurs, when the radius is about 3.84 and the height is about 7.67. And so that's the end of this, and we'll do some more problems, some optimization problems tomorrow in class. Have a great night.